Okay, welcome everybody to the last lecture. So today, oops, wait a second. So I think so far we kind of laid the foundation of, the collinear factorization picture, the PDFs, and what are the ingredients in a PDF global fit. The thing that we left out yesterday was the thing about the theoretical calculation, but I left it for today because the theoretical aspects are also like the theory frontiers that we have to face now. And I think they have to do with everything we said so far. And then I will guide you a bit through what are the state-of-the-art PDFs, the difference we have between, if you choose different PDF sets. And then I'll tell you another frontier, which is the one that I'm very interested in, which is the PDF and new physics interplay. And then I will mention a few things about the intrinsic charm, because there was some interest in the chat. This thing doesn't work, I think, but okay, I can move things here. Yeah, I know, of course. Sorry, it's morning. Okay, good. So we mentioned all these ingredients. So let's talk about the theoretical calculation that enter a fit. So what do we do? So the theoretical calculation enter here, no? So what we are doing whenever we try to determine the parameters of the Parton distribution functions, in whatever way we parameterize them, is to extract these functions, the parameter of F1 and F2, in case we have two protons, or just F1 if we have one proton, by minimizing the chi-square. So, but the thing that is important is that, this is what we want to extract, but then we have the sigma hat. So all the Partonic cross-section for all the observables that we put in our fit. Okay, so this is what I call the theoretical aspect. So the theory input is what goes into the computation of the sigma hat. Okay, and I want you to realize that, the sigma hat are always done by taking some external code or internal, whatever, that computes the Partonic cross-section, so the theoretical prediction for Parton I, Parton J going to something. And the standard global PDF fits are based on fixed order next to leading or QCD calculations. Okay, so typically we always take up to the second order in the expansion of alpha S. Okay, so this is very precise. There are a lot of technicalities which I decided not to tell you, because clearly it's not easy to interface the next to leading order code with PDF fit. So you have to do some tricks, some interpolation, some C-factor approximation, but I don't think it's very interesting for you. So on top of the fixed order NNLO calculation, you also set some specific values. For example, the alpha S you have here, you have to take alpha S at the mass of the Z. So this is your reference alpha S that you use in the theoretical prediction you have here. So you set a specific value for the mass of the W, the mass of the Z, the alpha electroweak. You choose a specific value for the CKM matrix element, for the heavy quark masses, and for branching ratios, and so on and so forth, okay? But all these things, so for example, the missing higher orders in the perturbative expansions and the uncertainty on the values of these parameters is something that is not included in the PDF error bands that I showed you yesterday. So typically, these error bands are only the experimental error. So you only propagate the experimental covariance matrix into the fit of the PDF. So how do we deal with that? So somehow all the PDF uncertainties are a bit underestimated, because we are keeping all these things fixed. Okay, so we don't vary them. And there is another problem, is that, the PDF fits are performed at next to leading order, but the new frontier for Partonic cross-section is next cube leading order. I already told you that some of the Higgs cross-section, for example, gluon into Higgs, or BB bar into Higgs, or the Drellian cross-section, these are known to the next order, okay? So the problem, whenever people do talks about precision physics, you can see that now there is a new uncertainty on top of the two that I already mentioned. So there is the PDF uncertainty. So this is, for example, the uncertainty on W production. Okay, so the yellow one is the PDF uncertainty that goes between 1.5% up to 5% at larger value of the mass. And then you have the PDF plus alpha, okay, whatever, the alpha S variation that you have here. But then you have another source of uncertainty, which is now becoming important, which is the mismatch between the order of your perturbative cross-section, for example, in this case, is next cube leading order, and the order at which you computed your PDFs, which is next leading order. So this green line, which before everybody ignored, but now that we have n-cube calculation is becoming important, is what is calculated like that. So somehow they estimate that the difference, the difference between the next cube leading order and the next leading order is estimated by doing PDF fits at next to next or next to leading order and divided it by 2. So maybe it's a bit of a over conservative estimate, but just to say that, you know, this is something that is becoming important. And the same, for example, for they are computing what are all the errors, the theoretical errors in the Higgs cross-section when you look at gluon-gluon fusion into Higgs. And again, on top of the missing higher order uncertainty, the PDF plus alpha S uncertainty, and so on, we have this component, okay, that becomes larger if we go to high energy colliders, for example, to these 100 TeV colliders. So one of the frontiers now is how do we deal with that? So how do we include the theoretical uncertainty in a PDF fit, and how can we compute next cube leading order PDFs? So what are the ingredients that are missing? So this is the first thing I wanted to say. So somehow we know a bit what is the theoretical uncertainty of a next to leading order fit, because you can do a fit by keeping the predictions to leading order. And this is, for example, the gluon that you get. So the gluon that you get if you use the leading order in the perturbative prediction is this green line. If you do the fit by keeping the predictions of next to leading order, you get the red line for the gluon. And if you go to the next to leading order, which is the best we can do so far, you get the blue line, okay? And all of these is fine that they are not compatible because they are based on different theories. So the partonic cross-section are computed with different perturbative orders. But the difference, for example, between the gluon at leading order and the next leading order tells us what is the theoretical uncertainty of the fact that we did not include the next to leading orders in the partonic cross-section. So this is huge. You see that instead from next to leading to next, the uncertainty is smaller. And we can compute, we can estimate the difference, the shift between the next to leading and the next to leading, which is this red line, okay, for the gluon, and compare it to the nominal PDF uncertainty, which is of experimental nature, which is instead this uncertainty, okay, the blue one. So if you compare them, you see that at next to leading order, the two uncertainties are comparable, okay? So at next to leading order, we cannot ignore it, okay? What about next to next? The problem is that we don't have the next cube, so we cannot do the same game, no? So we cannot associate any difference because we don't know the next order. So how would the gluon move if I was using a next cube leading order theory input, which by the way, we don't have yet completely, okay? So that's the question. So, and again, here there have been 3 very recent attempts, so like 3 different papers that try to tackle this problem. And I just want to flash, you know, give you the references for you to look at it in case you are interested, because it's one of the, I think it's one of the interesting problems to work on. So one idea is to, you know, this is the usual chi-square formula. So in this paper, it was presented and it was implemented only at next to leading order. So we haven't done it at next to next. I did it with some collaborators. The idea is that you construct a theory covariance matrix. So on top of the experimental covariance matrix, you add the theory covariance matrix. How do you compute it? You compute it by varying the scales, you know, remember the renormalization and factorization scales of the predictions. This is the 9-point variation. So you vary them up and down, you know, you have 2 scales, three possibilities. So you have 9 options not to vary the scales. So when you do that, you basically, so if you think about on the diagonal, the scale variation just gives you the scale variation uncertainty for a given prediction. But then on top of that, you have correlation because, for example, the factorization scale is the same for all processes that you put in. So when you vary it up, you vary it up in all processes. So the idea is that basically, instead of having the covariance matrix, which is this thing, which is a matrix that is a block diagonal matrix, because these are only the experimental correlation within each of the experiments, the one that we were talking about yesterday. If you include the theoretical covariance matrix and you add them up, you have the theory plus experiment that have much more correlation. So imagine this is a 5,000 times 5,000 matrix with lots of non-zero elements off diagonal, okay? So the problem becomes more complicated in terms of the inversion and so on, but you can use it and you can check what are the results. So at next to leading order, it's interesting. Actually, I already gave you these are the preliminary results at next to leading order, sorry. So what happens here at next to next is that it's nice because the normal PDF fit, when you include the theory covariance matrix, gets shifted a bit, especially in the small invariant mass region, which is the small x region, and the uncertainty becomes larger. So it is what we expect, more or less. We expect that the uncertainty with experimental uncertainty only are underestimated. You add another component, they become larger, and also they rebalance the experiment. So the experiment that measures something that has a large theoretical uncertainty are de-weighted with respect to the ones that are known very precisely. Okay, so this is the idea. Of course, in doing that, you're doing lots of assumptions. You're assuming some models on the correlation of the various scales. But okay, that's you have to have a prior if you want. Okay, so that's one of the ideas that is that people are exploring. Another idea, it's very colorful plot that I did with one of my postdocs was, so you can do the Monte Carlo sampling. I told you, before you can do it in the experimental space. So you just generate replicas of the experiments. But on top of it, you also do a sampling in the space of the scales. Okay. So on each of these replicas, so now you have a lot of replicas, let's say 8,000. And each of those has a different value of the scales. Okay. So you have to assign a prior probability on that. And then you determine a posterior probability by eliminating the replicas that have a worse chi-square. So somehow you let the data tell you what are the best scales for the experiments. So this is a bit of a, again, I don't want to explain it to you because it would take 1 hour and I don't want to do it, but just to give you a colorful plot and give you the idea that you can basically extend the Monte Carlo sampling on also a theoretical space and do a joint distribution. So this is a more kind of Bayesian approach, okay? So you determine the prior, you determine the posterior according to some criterion, and then you get a PDF uncertainty, which is the same. You compute it over all these replicas and it gets larger because you are expanding the sample. Okay, that's another idea. Finally, option 3, which has now been used by the MSHT collaboration to do this kind of game, so to include this sort of uncertainty and also start including the bits of the next cube leading order that we know, is that you add the missing higher order uncertainty as a nuisance parameter, and you fit this nuisance parameter from the data. So this is a good idea, but it's controversial in a sense, because some people think, yeah, but theory is theory and data are data. If we let the data tell us what the theory is, then there is no more independence between the theory and the data. So somehow we want a theory prediction, which is, if you want, independent. And so I think this is something that is nice, but has some controversies in a sense. It's a more extreme idea than that. You just tell the data that, okay, the very extreme values of the scales that give you a bad chi-square, you get rid of them. Here, you really let the data determine you what is the best value for these unknown scales, okay? So again, there are a lot of debates, there are very heated debates. Sometimes you might go to a conference and people like punching each other about that. But anyway, it's fun. So this is the thing. And the other thing here is that, so basically just to show tell you what I'm showing here. So these are these approximated PDF and QBellow PDF, and these are the next to leading order. So it's a bit weird because the PDF change a lot. So when you add these nuisance parameter, you let them fit from the data. So you have shifts that are rather large. So this is something that has not been understood yet. And there are lots of ongoing discussion. Also the NMPDF, we are including all so because at Next QBellow we have some ingredients, people are doing a huge effort. So there are theories to produce some splitting functions, the one that I told you, which are the kernels of the DIGLAP at next cube leading order. They are known in some of the limits in the phase space, and we have some calculations for some of the observables that go. So in principle, one could include the incomplete higher order uncertainty. And again, you will, if you go to conferences, you might hear NMPDF fighting again MSHT, because this is done in a different way and you get different splitting function on next cube leading order. So this would be the theoretical prediction that you reconstruct on the basis of the information you already have by varying all the unknown parameters. And you can see that NMPDF or MSHT have different results for this next cube LO splitting function. So I think, again, if you are interested, you should look at this and see how this discussion goes, because it's an ongoing discussion. It's a frontier, so there is not a finite answer. So we have to see what's going to happen in the next few years. But I think it's a very relevant topic. So we have to end up with a definite answer and understand what are the options there. Okay. Then another frontier that again has been explored partially, but not too much, more in the past than now. So the idea is that everything is done a fixed order, but some of you will know that when you have multi-scale processes, okay, so processes that involve scales that is not just the mass of the heavy object you produce, but for example, you have other heavy objects. So you always have ratios of two different scales. And whenever you have these two scales, there are logarithms that arise in your perturbative expansion, okay? So what it means is that this especially if alpha s times the logarithm is something big, is something of order 1, that's something I was discussing with some of you in the coffee break. The fixed order perturbative QCD is no longer justified. You have to expand on different parameters. It's like what you do in the Parton shower I was discussing with you. So you have to resum in order to rearrange the perturbative series. Instead of going 1 plus alpha square, you have to do this expansion. So alpha log to n plus 1, alpha log all to the n, alpha log times over L. Okay, so this is a different, what is called leading log expansion, next to leading log expansion, and so on. And there are different kinds of logarithms depending on the observables that we are fitting. So the problem in PDF fits is that you have a lot of different observables, and each one of them, in principle, in some regions, requires the resummation of different logarithms. Okay, so one could say, okay, let's take one of these logs and see what happens. No? So one of the logs is the threshold resummation. So for example, if you produce a particle, so let's say you want to produce a W and you have, which is 80 GeV, and you have only 90 GeV at the beginning, because you pick up two partons that has small x. So you have a center of mass energy that has just enough energy to produce a W. You have some threshold logarithm, okay, let's say just because you are at the threshold. So one thing that we did long time ago now, it was in 2015, we said, okay, what if we expand this cross-section in the leading log instead of the fixed order perturbation? And again, you see that this has an effect at large x, okay, because the PDF somehow, if you use a different theory, which enhances the partonic cross-section, because you're doing a product, PDF times partonic cross-section. If the partonic cross-section is enhanced by this contribution, then the PDF has to go down, okay? So this is the intuitive idea. So that's why when instead of fixed order, you do fixed order plus resummation, the PDF goes down to somehow compensate the plus contribution that you get from the correction you have on the partonic cross-section. Anyway, this is something that was done, but then was not pursued. But I think, again, because there is so much interest in the large X region, this is something that probably should be resurrected in some forms and kept it into account, okay? Okay, that's it for, then again, for theory prediction, I wanted to say another thing. So because we are at next to leading order in QCD, so far I said, I talked about QCD, but we know that basically more or less the electroweak coupling constant, so alpha, is about alpha s divided by 10, more or less. Now it's 1 over 137, whatever. So it's more or less 1/10 of 0.118, okay? So if you consider the next to leading order QCD corrections, you also have to consider the next to leading order electroweak corrections, because in the expansions, they are more or less of the same order, okay? So this is something that which is not done yet in all PDF fits. So it's yet another frontier. So because we are seeking for precision, we really need to include also these terms, which complicate the theoretical prediction that you have to put in a PDF fit. So, you know, whenever you consider electroweak correction, you have virtual diagrams that involve W and photon or Z. So you have lots of more diagrams. So the problem of electroweak correction is that they're much more complicated than QCD ones, because you have more electroweak bosons, okay? And then you have real electroweak correction, either from final state, so you have quark initiated, and then this quark emit a photon, or emit a W, or emit a Z, whatever you want. But you also have electroweak correction, which are photon initiated, and this is relevant for PDF fits. Why? Because you have to consider the photon as a parton, okay? Because in the same way in which inside the proton you can radiate quark, anti-quark, gluon, why shouldn't you be able to radiate photons, right? Because the photons do couple. So this requires an update into your DGLAP evolution equation. So sorry, before going there, let me just say that the photon initiated somehow, when you look, for example, at the Drellian cross-section for production of lepton, anti-lepton, so the real correction, so all the other corrections but these, they tend to push the cross-section down, no? So this is one, so the corrections are negative and large as you go to larger mass. When you put the initial photon, they become positive. So it's important to put both the photon and the other things, because otherwise you are overestimating the correction. So that you have two terms that compensate each other. So this is just to say that you do need the initial photon. How do you do? So it's simple. If you are at leading order, it's very simple. So remember that we calculated the splitting of a quark into a gluon, right? So this was the PQQ, the probability that the quark becomes a quark after emitting a gluon. You have to do the same for the photon. So it's the same thing in a sense, the PQQ. So the function that we calculated is exactly the same. The only thing that changes in this case is the alpha. So here you have alpha S and here you have alpha electromagnetic, okay? But it's exactly the same functional form. Again, also for this is exactly the same. What you don't have is the P gamma gamma. So because the photon doesn't couple with itself, it's an abelian theory. So the point is that whenever you do the evolution of the gluon and the quark, you have to add these terms. So this splitting of the photon into a quark that I just shown here, okay? So you need to do some order, so counting of the perturbative orders that you're adding, but basically you have that, you allow the possibility of having initial photon and you have the possibilities that the quark split into a photon, okay? So everything mixes up inside the evolution of the PDF inside the quark. So this is something that many people have done. What changes? So clearly, if you add another parton, you're taking away some of the momentum from the quarks and the gluons, because you are letting another parton carry some fraction of the proton momentum, okay? So there are differences. You don't just add a new parton. You add a parton, you subtract something to the other partons, okay? And this is something that, again, depends on X. But basically what you can see here is that, okay, 0 is nothing changes. But so as you go to large X, basically the gluon distribution, the up, the down, and the strange distribution becomes smaller up to a factor of 1% because of the fraction of momentum that is carried by the photon instead of by them. So they borrow some of the proton momentum to the photon. Okay, so there is a change also in these distributions. But the point is, how do we determine the photon PDF? So how do we determine the photon PDF? The problem is that the photon interacts weakly with things, much weaker than the quark and the gluon. So how do we do that? No? So the first time people were doing some model for the photon, like there were some theory, yeah, okay, whatever. But this was not really, in a sense, it was not taken too seriously because these models were just models, they weren't coming from first principles. So then I remember, I don't know, 10 years ago with NMPDF, we said, okay, let's put it into a fit. So we just add another neural network for the photon, and we let the data tell us what is the photon inside the proton, okay? That was a data-driven idea. And then there was a breakthrough, which I want to tell you because it's very interesting, that instead allowed us to compute the photon really from theoretical principles. So I tell you the story because it's a nice story. So what are the processes that can give us information about the photon? If you think about a data-driven knowledge, you have to think, what are the processes that have a different cross-section if they have a photon in the initial state, okay? So, and these processes are what I showed you before. For example, the W production, but also top pair production. So the W production changes if you have an initial photon, and also the top pair production changes significantly. So the game you have to do to think, okay, what are the processes that can give me information? You calculate the correlation coefficient between the photon and the cross-section. If you have correlation, it means that adding this data into your fit, you might hope to get some information about this PDF that you add, okay? But anyway, the results were not really nice. So these are the replicas, and you can see basically that has a huge, so they're gray, I don't know if you can see them, but basically this is small x, what's the difference? Yeah, it's just the photon PDF, you just look at it with two different scales. But basically, you see that there is a huge uncertainty. So the replicas go everywhere. So this means that really the data don't give much constraints on the photon, okay? At least the data that we have so far. So unless you put some theoretical input model, you have a huge PDF uncertainty on this parton that you add into your fit, okay? But then there was this breakthrough by Manuhar and other Nazon, Salam, and Dandrigi, and they had so I encourage you to read this paper if you have the stamina to do so, because it's a very nice one. Because the idea was, they say, but okay, we know that QED is a perturbative theory down to low scales. So the photon must be computable perturbatively if the input is known. So what they do here, so they imagine we have a cross-section for the production of a heavy supersymmetric lepton in some E+ collision. Okay, so they took any process, whatever. So it's a process of, I don't know why they chose this, but I think because they needed something heavy in the final state, whatever. And this process, I just tell you the idea, they write it down in the partonic model. So they just use the improved QCD model that we wrote down. So as a sum over sigma hat times F. And in this F, they include the initial photon, okay? And they write it down as a sum of structure functions, okay? In the same way, so somehow, so this is just the structure function formalism that I mentioned in the first part of my lecture. And if you do it using the photon, you have to keep some extra terms with respect to what I told you, but it's the same idea, no? So you have an F2 and FL, whatever. And on the other side, you have the parton model with the photon. And then they simply equate these two equations, okay? And they extract an equation for the photon, okay? And they prove you that you can do it because there is, so basically that there is no need to fit it. So you equating these two different ways of computing the cross-section, you can extract theoretically the F gamma, so the distribution. You have to read the paper because it's complicated, but you know, somehow it's a nice exercise. So to use what we did in the first lecture, so both the parton model and the structure function formalism and extract something out of it, which is the F of the proton, the PDF of the proton, or the photon, sorry. And the second interesting thing is that if you equate the two expressions and find analytically the PDF of the proton, then the proton becomes something like that. So X times the proton is some integral over these quantities. You have alpha, you have some kinematical variables, and then you have F2 and FL. These are experimental input. Okay, so they take the structure function as a known input from the experiment. So the error on this photon is just the error on the structure functions, which, however, are known really well. So that's why the error on the photon becomes so small once you add this theoretical input. And the other thing which is interesting is that this integral goes up to x equal 1, which means that in this integral, you don't have only the structure function from deep inelastic scattering, you also have the elastic component of the structure function that you looked at in other lectures here, okay? So you have to put together some of the elastic scattering, quasi-elastic scattering, and the deep inelastic scattering, okay? And these are all inputs that go into your analytical formula for the photon PDF, okay? So I really encourage you to have a look at that, and then we can have a chat on Slack if you have any questions about this paper, because I think it links nicely with everything you have done in the school. And the effect was amazing, because you see that now the LUX QED, which is this green thing, had an uncertainty of only whatever, like 2%, 3%. Well, before it was 100%. So it was really breakthrough in terms of precision. So now we really know the photon. And then with an MPDF, we say, okay, what if on top of this you add some data? So the data plus theory, it doesn't change much, but clearly the more data you have, the more you can constrain further the uncertainty in the usual sense, okay? So I think this was a nice story on how thinking differently about a problem, you can get a breakthrough. Okay, very good. Any questions about this part? Radiative correction. Yes, so so you're asking if when you add the photon PDF, you have to add radiative correction. Yes, the answer is yes, because if you want to add, so the photon, remember the big picture we started from, you need an initial photon, because if you want to add the electroweak corrections to the processes that you include in a PDF fit, you need this component as well. But once you have this component, it's not done. On top of it, you need the final state radiation, which is these diagrams over here, the virtual corrections, and so on and so forth, okay? And again, there are a lot of technicalities, because it's not easy to put all this information inside the fit when you have to compute fast many times the same thing to fit the parameters. And here we go into the realm of all the interpolation grids and all this stuff, which is, if you want, is boring from a conceptual point of view, but without it, we can't do anything. In a sense, I spent 2 years of my PhD doing a boring thing of just finding an interpolation, because otherwise none of this fit would be possible. Okay, here quickly. So I think, okay, the problem is, I just wanted to show you that, again, this part, probably it's obvious, and maybe I don't have to spend too much time, but, you know, what do? You know, if you are someone as a physicist, you're an experimentalist, a theory, you want to use the PDF set, and you have lots of different collaboration who give you the best gluon according to their knowledge, you know, so according to their methodology, this is the best fit for the gluon. That's the uncertainty, okay? Do you pick one at random? Do you take the envelope of all the predictions? And again, so here I wanted to show you some examples. So this is the recent NOMAS paper, where there are some of the PDF, especially, you know, here, most of the PDFs that are the ones that include LHC data. So that's why you don't see, for example, CJ15 or JUMP PDFs, is because in all this comparison, they always look at PDFs that are, if you want, tuned for high energies, because they take input from the LHC data, whatever. And then again, so each of these, so these are the prediction for the Higgs resection, gluon into Higgs, or TT bar Higgs. Okay, these are two processes. And these are the 95% confidence contour. there is a bit of correlation because the two processes have the same PDFs in some of the input. So, and you can see that, all of these are the 8 PDF sets that are considered as an input. And, lots of them agree. So they're a bit in the middle. So the uncertainty is this. That's the PDF uncertainty for TT bar Higgs. And this is the PDF uncertainty for Higgs production, okay? But again, so first of all, if you decide to take also the Atlas PDF, this gives you much. So if you decide I take the envelope, then the uncertainty would be like that. If you decide I take NMPDF 4.0, the uncertainty would be like that, okay? Or if you decide to take another one. So that's a very important problem. How do we, and there is not agreement on that, So either you say, I sell you my PDF set because it's the best, use it and don't care about the other ones. Or some people want to be over conservative, they want to take the whole envelope, but then you see that then our theoretical uncertainty becomes huge, no? So it's, and you see that it's nice, this paper, because there are lots of different combination of observables, and you can see how the spread is big. But what you notice all the time is that NMPDF 4.0, which is something that I worked on, is the one with the smallest uncertainty, much smaller than anything else, because it has this methodology based on deep learning. And others have larger uncertainty. So you have to really look into the details. The only thing is really to look at what are the data included, what are the statistical treatment, what's the parameterization, what's the scheme, what's the order. So, and that, again, something I don't have time to go through, but you have to somehow think, what is the thing that I need now, and what are the differences? Do I trust the way in which PDF have been computed, and so on and so forth? So I think there is no other way than to do that. And yeah, anyway, I gave you a summary for your own reference. You can go back to it. I might have made a mistake. Please point it out.
We have Tevatron jets.
Okay, so I did it yesterday night, really late. Okay. Okay, this has to become green. I don't think they have. Do you know? Do you have Tevatron jet? Not. Okay. So I will change that. Okay. And again, I just try to relate with what we said about parameterization and statistical treatment. Very good. And yes, and the other thing I wanted to say, that there was a golden time in 2016 where the kind of collaboration that had the same data input, we had the same luminosities, so the same PDFs, and everybody agreed. There was a happy time where people were all friends with each other, and then suddenly people updated their things and the agreement went away. So now we are back fighting again. So just that's a sociological thing, but somehow there was a reason. There was at some point, you see that if you were computing, for example, gluon into Higgs with any of the 3 kind of super global PDF sets, you were getting the same answer. Now you don't. Okay, so now people went back to fight and to try to understand the internal differences. And the same happened. So the quark anti-quark was already different, but now it's better if you exclude the Atlas PDF and the CT18. Okay, I don't know, but we can talk about it later. I don't want to spend too much time here. Okay. Anyway, yeah, there was also a benchmark, but okay, I don't want to bother you with that. But really, I think the question is, so let's take, for example, NMPDF. So we are making a claim that we have a 1% accuracy in lots of regions. So, but the point is, can you trust this kind of accuracy? So when we say that I give you a PDF with a 1% uncertainty, can you trust it? Then there are some projections that if you add the high Lumi LHC data, you go to 0.5%. Can you trust that? So the problem is that you don't want just things to be precise, you also want them to be accurate. So it's not enough that they're all close to each other, they want them to center the center of the target you want. So I think that on top of benchmarking different PDF sets, each set must deal with inconsistency. So if I tell you that this is my best gluon, and then the next release, I give you a gluon which is 3-5% outside the error band that I told you earlier, I have to tell you why, okay? And because here is the problem of inconsistency. So there might be inconsistent data, what we discussed about yesterday. There might be updated parameterization. Is it justified or not? There might be differences in the fitting methodology minimization. Has it happened in NPDF 2.3? or some changes in the theory. So one has to really understand where the incompatibilities come from, because we might discover something new, okay? And we might understand the differences. That's it. I don't want to go too much into it, but just to say that these are all hot topics and sources of lots of discussions. That's it. I have 10 minutes perhaps to tell you something that I got really excited about in the last 3 years, which is this thing about PDF fits and new physics interplay. So there are 3 aspects that I wanted to mention, and I think all of the 3 of them are all very important. I will flash them onto you, and then you can look at the references or discuss with me later on if you're interested in. So new partons, as we said about the photons, if you include, for example, electroweak correction, you must include the photon among the partons, okay? And when people still believed in supersymmetry, there were this very interesting study by CTEC. He said, what if we have some supersymmetric particles can be part of the proton wave function? Can we have some super parton? Okay, so some of the SUSY particle that is part of the proton. And how do we compute that? So there were these nice studies they were showing that if you have a light supersymmetric parton, this would modify the Diglap equation and also the running of alpha strong, because especially if it's a colored particle. So they were looking at gluino and squark. So this would be colored particle that would change the renormalization group equation for alpha S and the Diglap. And it was interesting because at the time, comparing to the data, they were excluding the very low mass ranges for supersymmetric particles, because they would have modified things so that the collinear picture would not have worked anymore. So that's a nice thing. Recently, I worked on this paper. They say, okay, fine, we cannot have colored particles because these have been excluded and we haven't found any supersymmetry, any colored particle. But what if we have some weakly interacting particles, for example, a dark photon? So what if you had a dark photon which weakly couples only to the quarks, okay? So then you can have some effective field theory where you have a leptophobic dark photon, which is weakly coupled, and you can add it via some effective Lagrangian. And it's interesting because it's a very simple game, if you want. It's exactly like adding a photon, but you produce it at threshold, so above the mass of this dark photon. And that's the game that we did, but without thinking that we would have found much. And instead, the interesting thing is that it does give you some bounds on the phase space. So looking at the data, especially in the high Lumi, you can exclude some of the parameter space of the dark photon in terms of mass and coupling. So these are the 2 lines that we found in the conservative and pessimistic scenarios. So if you're very optimistic here, it gives you a constraint in this region where the kind of direct searches or indirect searches for dark photon were not present, and also it lowers a bit the bounds on the gamma decay. So I think this thing of playing a bit with, weakly coupled new physics model and how they can change your PDF evolution and what this tells us in terms of limit is still a viable option to explore some of the parameter space of new physics. Another thing, it's about, again, it's the same thing that I said on the first day, so I will not spend too much time, but it's that given that the high mass tails, all kinds of tails are always affected by large PDF uncertainty because we don't know really well the PDF at large X. So we were doing recently this study, I forgot the reference, but for example, when you look at the forward and backward asymmetry, there was this Collins-Soper variable. So you just look at the Drellian cross-section in the cosine of this theta star angle, and you look the forward versus the backward cross-section. This is something that can give lots of signatures for new physics model. But the problem is that, for example, if you use an MPDF or 4.0, you have a huge uncertainty, like 30% to 20%. So, and you don't really get out of it, I think, by keeping including high energy data from the LHC, because of the third problem that I will mention later on. So I think here we are lucky enough because the EIC can really take data in a region which is very complementary with respect to the current DIS data at low values of energy, where there are no contamination for new physics. And really, you know, there were some studies on optimistic and pessimistic scenario. The uncertainty of the upquark in the very extreme region of 0.7, 0.8, 0.9, which is the one that we need for the forward-backward asymmetry, can really be reduced by a very significant factor. So this, I think, shows how important it is for new physics at high energy colliders to get a low energy input that can help you constrain in a way that is not contaminated by new physics. And this is the next bit I wanted to mention, which, yes. Do you want a microphone? Or use it?
No, just adding one thing, we don't need to wait for ACAC will be great, but not necessarily for the high X. There are limitations that are still to be worked out, but there is a huge amount of data from JLab now, and at 12 GeV, they will come out more that go inside the large X region, even more at the large Q square, so really in the large X and even elastic region. And so you have a different focus or so, but there is already a lot of data there, and knowledge how to take into account all those things. Now CJ Gem is doing that. There is Aliokin and Kulagin and Petty who also look at that region in particular. So it's very worthwhile to look at the data that is completely excluded by your dashed line over there. So it takes effort to put that line down and building knowledge inside your collaboration. But if there is a subgroup of you interested in that part, I think it's a very worthwhile thing. Absolutely. And I would welcome a new enemy, I mean, a new competitor in that region. So far,
no, because again, all these comparison, we always do them for the thing that include LHC data, because that's a focus, because we don't understand lots of things here, but and we somehow have been a bit lazy, and that's something to be, you know, to, for example, include all these higher twists and all the things that you need in order to lower that by collaborating with you guys who do this kind of thing. So I think, you know, this was just an example because it was done with exactly using the same technologies. But if one improves the theoretical input at large X, which is something that you have done and we haven't done, then there will be much more input to put inside that. I agree with you.
It's a great example here. And it's also, just for you, it's not a problem of laziness. It's a problem of physics focus and people, how much work power you have.
Exactly.
Which there are two couple problems. So it's
yes.
but it's I was just pointing out there is much more data that is already available. We don't need to wait 10 years.
No, of course. Yeah. Again, it's I think it's a push towards investing in something which is very important also for the high energy side. So yes, and something, I don't know if I have time to say anything. Yeah, so let me just try to summarize. What if new physics lives at very high energies? Okay, something that we are never going to be able to spot at the LHC. Okay, so the interesting thing is that still, even if you have something that lives at high energy, it still would change the tails of the high energy distributions, because you would see something. You can use effective field theory expansion in the scale of the heavy new physics. And you can see that this thing, if you are at high energy, especially with operators that have energy growing effect, has an effect now. So you can somehow, using the effective field theories, have a telescope into something that lives at much higher energy, but leaves some signs here. And this is the goal of all these math operators. So the idea is that on top of the standard model, you add dimension 6 operators that characterize in a kind of agnostic way the effect of new physics that lives at the scale lambda, okay? And you add these corrections to the standard model cross-section. So the corrections that come from the dimension 6 operators, okay? And there is a huge activity at high energy about these things, no? There are lots. So the problem is that the full basis of operator is done by 2,500 operators. So it's impossible to fit them all. But you can do some flavor assumption to reduce the basis and so on. So there are fits of these coefficients in the hope of finding that some of them are different from zero. Actually, if you include the W mass anomaly from CDF, they have done some fits and many of them are different from zero. So if you trust, so because so far the picture is the following. So this is, I think, the most global fit we have. So we have 36 Wilson coefficients, and you determine them by looking at the top data, the Higgs data, and so on. And you see the bottom line is that they are all compatible with zero, but there is room for new physics. So in a sense, there are some large uncertainties. So the truth might be somewhere in between zero and something zero. Okay, very good.
Orange ones are a bit deep.
The orange one, yeah, these here, exactly. Yeah, but these people, so this is the EFT quadratic, which is 1 over lambda to the 4th. So people say you have to, for example, Frank and Raja, they say, you know, you have to add dimension 8 if you want to go quadratic. So if you look at the linear, which is consistent expansion, which is just interference between the standard model and 1 over lambda squared, everything is compatible with zero. If you add the quadratic, you have some indication, for example, yeah, this is cool, so this is different from zero. But, you know, people don't trust it so much because we don't have the dimension 8 input as well. So there is a debate, whatever. But my point is, okay, these coefficients that modify the high energy tails are there in the theoretical prediction also of the observables you put in a PDF fit. And at the moment, we do things inconsistently because in a PDF fit, you fit the parameters theta of the PDF and you set all these coefficients to zero, as if you don't give any possibility for new physics to show up in the high energy tails. When you do a fit of these coefficients, you take some fixed PDF and you let these coefficients vary, okay? Not in the PDF, but in the partonic cross-section. So somehow there is an inconsistency between the things we do in a PDF fit and in a SMEFT fit. So the group I'm working on, so I'm working with this group that is based in Cambridge with this project, and we are trying to answer this question. So clearly, in principle, the low energy physics is separable from the high energy scale physics. However, because we use this high energy new data, this might influence the determination of low energy quantities like the PDFs. So somehow the questions are we sure that we are not observing? So for example, if you look at the NMPDF with or without the LHC data, you have a big shift. Isn't this because we are just not considering this kind of effect? So that's the question. So what if we consider the effect and given the possibility of new physics to show up in the higher energy tail, would this change our fit of PDFs? And would the fit of the coefficients change? Yes or no? And here, when I say the complexity of the LHC, I'm meaning this thing because lots of the data that we use in the PDF fits are also used in the fits of the SMEFT coefficients, okay? So these are the questions. Now, from the point of view of the PDF fits, how do we make sure that new physics effects are not inadvertently fitted away in a PDF fit? And I'm actually working on a paper that I'm going to publish in 2 weeks that I show you in a given scenario, you can fit away the effect, for example, of a new W prime boson. You have a perfect fit, beautiful, completely different from a standard model fit. And it's as good as the other. So that's a very interesting question that we just found a smoking gun that it is possible. And from the point of view of this math fit, should I make sure that I'm using a clean set of PDF that doesn't have any of this contamination? How to define it? You know, one option is to take only the low energy fits because they don't have any contamination. Or how would the bounds on new physics change if I was consistently using PDF that include the fit theory prediction computing, adding the same operator? So, and one way of doing it is to do simultaneous fit, where you fit everything together. And I don't have time to tell you, but that's something that we did in the Drellian sector. And these are the bounds on two operators. You can see that if you don't include the PDFs, you find the orange bound. If you include the PDF, you find the green bound. So you have more space for new physics if you let the PDF vary. And the other thing, the PDF uncertainty by letting this coefficient vary increases because you let this option, this new physics option kick in. And also, okay, I don't have time, in the top sector, you have the same thing. Good. I don't have time. So let's say that I can, at the break, I can sit here with some of you. I just wanted to show the intrinsic charm. Basically, this is what I said last time. I just want to flash the result. I said that the common assumption in the PDF fit is that the static proton wave function doesn't contain charm quarks. You only have intrinsic up, down strange, and anti-quark, but no intrinsic charm because the charm is heavier than the proton, okay? So you generate it perturbatively out of a gluon. That's what I said yesterday. Inside the quark, you have the evolution, you only have the perturbative component, okay? But there were models, Brodsky and collaborator in the 80s that were showing that actually in many models, you do have an intrinsic component of the charm inside the proton. So you have this extra operator with CC bar inside the proton and so on. And there were many years. So basically the results that some of you pointed up is it possible to disentangle an intrinsic charm component from a perturbative component in a PDF fit? So, and some of the NMPDF, I was not in the paper, but some did that. In this paper, so basically they added an extra input to the neural network. They did a lot of theoretical things to extrapolate, to really subtract the perturbative component. And this is the result that was published in Nature, in a sense that it shows that actually there is more than 2 sigma evidence of an intrinsic component of the charm. And this is a very interesting result. There will be a lot of discussion as well. And I can talk to you later if you are interested in. Okay, so I want to conclude by saying that I hope that I showed you that there is lots of interesting things inside the proton. There are a lot of different topics that I touch upon, perhaps too many, but I think there are lots of very beautiful things to see. And I can say, as something encouraging, hopefully for you, that after 20 years nearly spent looking at the proton structure, I really share the enthusiasm that Feynman was talking about when he says, you know, the same thrill, the same awe and mystery come again and again when we look at any problem deeply enough. With more knowledge comes deeper, more wonderful mystery, luring one on to penetrate deeper still, and blah, blah, blah. So I think it's a grand adventure. Thank you very much.
The PDF fits that you showed, you said you were comparing with the theory. So the theory that you were looking at, is it just the perturbative? Do you also have lattice QCD expectations for the lattice QCD predictions? No.
No, only perturbative thing.
Okay.
So this is a new frontier that I didn't have time to talk about in principle, but I think the most reasonable thing to do at the moment is to add the lattice prediction as data, because they're all integrated. So they give us the momentum of some PDFs. And if you want, in a sense, that's something that I think if lattice keeps evolving, eventually they can give us enough points that we don't need to do all this stuff. It can really be extrapolated from first principles. I'm a bit skeptical about the theory. You know, I think that this quasi-PDFs, I'm not sure how they compare with these PDFs. And there are still some things that, but exactly, there are lots of PDF lattice papers and there are lots of developments. No, there are more, I think, right.
This comes from a series of workshops, and there are 2 sort of reviews if you're interested in that. And it gives you an overview of the issues on the side and blah, 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 blah.
Yeah.
So, it's sort of entry points, if you wish.
Yes.
And, some GEM collaboration work that try to put the data inside it, what it gains. It's also about a lot of issues, how much in class, the systematics on the
Exactly.
on the lattice calculations, and then there are various things to take into account, but yes,
yeah, it's a very interesting development. So we have to see how it goes. Yeah, JAM or CITEC, they did some point probably.
More questions? You mentioned something about the PDF fittings using data and like how that was like controversial. is the concern there that like you're relying on like the quality of the data and like you're dependent on the errors in it?
Yeah, here I'm just saying that this is a purely theoretical thing. No? So whenever you compute something, you have whatever some coefficient, and then you have so you have the expansion, no? Mu r, and then you have if you want the partonic cross section at order 1, which depends on mu r, mu f, and so on. So in these scales, so this comes from the UV renormalization of alpha s, and this comes from the collinear, the absorption of the collinear singularities. No? So that's the collinear factorization part. So all of these things have a theoretical origin, so they have nothing to do with any data. So in a sense, this is a theoretical ambiguity that we have in our perturbation theory, because we have some infinities that come either from the UV region or from the collinear region, and we absorb them by redefining the bare coupling constant with the bare PDFs, okay? So in this approach, they, if you want, add not exactly mu r and mu s, but they add some combination of these as some fitting parameters. So you let the data tell you not only the parameters of the PDF, but also what is the best, it's a simplification. No? So you get mu f and mu r, which are theory parameters determined by the data. So then the controversy is, if we want to compare a theory with the data, but you let the data tell you everything about the theory, so how can we find something new? No? So because we let the data tell us what theoretical prediction should be. So I think that they should be kept separated. So there is an uncertainty, which is of purely theoretical origin, that gives us a range where the standard model prediction could be, and we could keep the range safe. And then the data tell us something about non-perturbative parameters, because these are perturbative parameters. I know exactly where they come from. That's a controversy.
I see. Thank you.
So about the photon PDF, I was thinking about, so since the PDF is like a probability of finding something, so we are thinking about the photon as a parton. So are there any constraints, like energy constraints in the scale, like when this is more, when the probability to find it is higher, is there? Like,
yes.
Did you do those works also basing on some constraints that could be an energy constraint or any other constraints? I'm thinking about.
In the case of the photon, in a sense, it's not a constraint, but it's the evolution. So even here, sorry, oops. Okay, I don't have. Okay, imagine. So this is the photon, whatever. That's a big uncertainty at a given scale. If you put it as a parton, it does acquire a scale dependence exactly like the quark and like the gluon. So if you want, the scale constraint is the fact that it does evolve according to the, according to the Diglap evolution that I wrote here somewhere. So in a sense, it does have a very strong scale constraint, because if you go back, I don't know why, I pressed the wrong button. If you go to just the next, okay, cool. Here, so the constraint is this, so it's a bit hidden, but it's what comes out from the solution of this equation. So the photon is different depending on the scale at which you're looking at it. Okay, it evolves with the scale exactly like the other partons. If the photon was heavy, like the dark photon, then you would have an extra constraint, the fact that you cannot produce it below the energy that is equal to its mass. But the photon is mass 0, so we have it at all scales. Yes. There was a question there. Then
I was faster.
Yes.
On that image that you showed many feeds of the PDFs, and they are all kind of not in the same place. They do not. What would we need to do? Not this one, the feeds one.
Okay, here.
Yes. What would we need to do, both in theory and experiments, to make them converge, or for a way to pick the right one out of this?
Yes, so that's a very good question. So this, for example, this is a recent benchmark that was done between 3 collaborations. You see, this thing improves if you use the same data set. So for example, if everybody was using the same data set and treating the data in the same way, that would already be a big point of convergence, okay? Still, even here, you see that, for example, QQ bar luminosity, okay, in the extrapolation, there are some differences, but in the data region, they're closer to each other. The uncertainties are different because the uncertainty really depends on the methodology. The devil is in the details. So, for example, CT has the tolerance, which is different from MSHT, and MPDF doesn't have a tolerance. It has the stopping and this methodology that is based on whatever deep learning model, okay? So the difference, this is the difference in the uncertainty. This you can understand based on the methodology, no? So, and again, the equation conservative is good. I don't believe in it, no? Because if not, we just blow all the uncertainties by a factor of 10 and everybody agrees. So, but there must be something in between, no? The conservativeness and the reliability.
Yeah. As a follow-up, how much precision is enough? Like, are you gonna work on more and more precision until we have 0.1, 0.2% or even lower? Or is 1% enough to discover the new physics that you were talking in the end?
Yeah, that's a very good question. So I don't know why there is a 1% target. That would already be great, you know, if all the theoretical uncertainties are 1%. But I think there is a saturation eventually because somehow you keep adding data. Either they're all compatible with each other or you cannot really go down too much, you know? Otherwise you're biasing the result. The other thing is that all these components of the uncertainty that we have ignored so far should really go, because, you know, if we really push the PDF experimental uncertainty down to 0.2%, we know that the theoretical uncertainty is at least 0.5. You know, so I think the first effort is to be more reliable in terms of what we put inside the uncertainty. And the second thing is, okay, where is the saturation point is? I don't know. It depends on the experiments, yeah.
Thanks.
Let's thank Maria.
Okay.
Oh. We have 10 minutes break.
Yes, thank you very much.